Look up at the night sky. You see a vast, dark canvas dotted with points of light, a scene that has filled humanity with wonder for thousands of years. We are told a simple story, a massive explosion, a big bang, and over billions of years, stars, galaxies, and eventually us came to be. But what if that story, as grand as it is missing some of its most incredible pages? What if the very origins of our universe hold secrets that have been overlooked, mysteries that challenge everything we think we know? We live in a time of unprecedented discovery, where telescopes peer back to the dawn of time and physics probes the laws of existence itself. And yet, some of the most profound facts about our cosmic beginning have slipped through the cracks of popular understanding. These are the forgotten facts, the puzzle pieces that don't quite fit the standard picture, and they point to a reality far stranger and more magnificent than we ever imagined. This video is a journey to uncover those pieces. We are going to explore 25 forgotten facts about the universe's origins, each one a revelation that bends the mind and redefines the possible. We will venture beyond the textbook explanation of the Big Bang to ask what, if anything, came before it. We will confront the eerie fine-tuning of the cosmos, where the fundamental constants of nature seem perfectly calibrated for life against inconceivable odds. We will examine the silent clues hidden in the cosmic microwave background, the ancient light that is the afterglow of creation itself, and question what it is truly telling us about the universe's first moments. This is not just a list of trivia, it is a deep dive into the frontiers of cosmology, a field where the answers we find only lead to more profound and thrilling questions. So prepare to have your perspective shifted. We are about to pull back the curtain on a narrative filled with cosmic inflation, quantum fluctuations, and the potential for a multiverse. This exploration is for anyone who has ever gazed at the stars and felt a deep, resonating curiosity about our place in it all. It's a story of how we came to be, pieced together from clues that were always there, waiting to be remembered. This is the story of our universe's greatest secrets, and it begins now. Our journey into the forgotten facts begins not with an image, but with a sound. A sound so immense, so powerful, that it makes the loudest thunderclap seem like a whisper. We often picture the Big Bang as a silent, explosive flash of light in the void, but in reality, the birth of our universe was anything but quiet. In its first few 100,000 years, the entire cosmos was a searing, dense soup of particles and energy, a plasma so thick that light was trapped, bouncing endlessly from one particle to another. Within this churning, primordial fluid, the force of the initial expansion created colossal waves of pressure. These were not waves of sound as we know them, traveling through air, but fundamental vibrations rippling through the very fabric of space-time itself, compressing and rarefying the hot plasma in a cosmic rhythm. Scientists refer to these as baryon acoustic oscillations, which is a complex term for a simple, powerful idea. The universe was ringing like a bell. These pressure waves traveled outwards from the initial density fluctuations, creating peaks and troughs of matter that would eventually become the seeds for the largest structures we see today, the vast cosmic web of galaxies and clusters. The evidence for this primordial symphony is etched into the oldest light we can observe, the cosmic microwave background radiation. This afterglow, which we see as a uniform, faint glow in every direction, contains tiny, telltale variations in temperature. Those patterns are the frozen fingerprints of those first sound waves, a snapshot of the universe's acoustic landscape at the moment it became transparent. Using sophisticated data analysis, researchers have done something truly extraordinary. They have translated these ancient imprints into an audible frequency range our ears can perceive. The result is not a gentle hum or a melodic tone. It is a deep, bass-heavy roar, a drone of unimaginable power that would have been physically deafening had there been any ears to hear it. This sonic fossil gives us a completely new way to experience the universe's violent birth. It moves the event from an abstract concept in a textbook to a tangible, visceral phenomenon. It reminds us that creation was a physical, turbulent process, a chaotic concert whose echoes are still woven into the fabric of everything that exists, including us. But if the universe began with a deafening roar, the ingredients for that symphony were far stranger than anything we find on the periodic table today. We often think of hydrogen as the starting point, the simple, pristine atom from which all else was forged in the hearts of stars. But this leads us to our second forgotten fact: there was a time before hydrogen. For a brief, spectacularly violent window in the universe's first few minutes, the very concept of a stable atom was impossible. This era, known as primordial nucleosynthesis, was a frantic race against time and temperature that set the stage for everything to come. To understand this, we need to rewind to a point just a fraction of a second after the beginning. The universe was not a gas, it was an unimaginably dense and hot plasma, often called the quark-gluon plasma. In this state, the fundamental building blocks of protons and neutrons, quarks, and the gluons that bind them roamed freely, too energized by the intense heat to combine into stable particles. It was a seething ocean of pure potential. As the universe expanded and cooled at a breathtaking rate, this chaotic sea underwent a dramatic phase change. Around 1/1,000,000th of a second old, the temperature dropped enough for quarks to finally bind together, condensing out of the plasma to form the first protons and neutrons. Now the real drama began. For the next few minutes, the entire cosmos acted as a nuclear fusion reactor, but one operating under conditions of extreme chaos. Protons and neutrons collided furiously. Initially, the balance of power favored neutrons, but neutrons are inherently unstable on their own. If not bound into an atomic nucleus, a free neutron will decay into a proton, an electron, and a neutrino in about 15 minutes. So there was a frantic competition. The universe was cooling rapidly, and neutrons were trying to find partners to form stable nuclei before they simply vanished. The first successful unions created deuterium, a heavy isotope of hydrogen consisting of one proton and one neutron. But in that intense heat, deuterium nuclei were extremely fragile, often being smashed apart by high-energy photons as soon as they formed. It was only when the universe cooled further that deuterium could survive long enough to act as a stepping stone. This is when the narrative truly defies our everyday expectations. Helium, an element we associate with birthday balloons, was actually the first complex element to exist in any significant quantity, forming before most of the universe's hydrogen atoms were even complete. How is that possible? Because a hydrogen atom is a proton orbited by an electron, but stable atomic structure couldn't form for another 380,000 years when the universe cooled enough for electrons to be captured. The helium produced in those first 3 minutes was just the bare nucleus, 2 protons and 2 neutrons flying through a sea of particles. This period of primordial nucleosynthesis was incredibly brief, lasting only about 17 minutes. When it ended, the universe's elemental composition was set, about 75% hydrogen nuclei by mass and 25% helium nuclei with trace amounts of lithium. Every other element, from the carbon in our bodies to the iron in our blood, would have to wait billions of years to be forged in the furnaces of stars and the cataclysms of supernova. So the next time you look up at the stars, remember that their primary fuel, hydrogen, was not the universe's first creation. It was the leftover ash from a fiery 17-minute frenzy that determined the ultimate fate of the cosmos. Yet from that chaotic symphony of particles and light, our universe then entered its most profound and silent chapter. After the release of the cosmic microwave background, the universe did not suddenly fill with stars. Instead, it plunged into an era of unimaginable darkness that stretched on for 100 million years. This is our third forgotten fact, a cosmic dark age so vast and quiet that it makes the entire history of human civilization seem like a fleeting blink. The universe had cooled dramatically, and for the first time, protons and electrons had combined to form complete, neutral atoms of hydrogen and helium. With no free electrons left to scatter it, light could now travel freely across the cosmos. But here lies the great paradox. The universe had finally become transparent, yet there was almost nothing to see. Picture an expanse of near-total blackness, an endless, featureless sea of gas. There were no stars, no galaxies, no points of light to punctuate the overwhelming void. The only illumination was the fading, uniform glow of the cosmic microwave background, which was shifting from visible light into infrared and then microwave wavelengths as the universe continued to expand. The temperature plummeted to just a few tens of degrees above absolute zero. It was a cold, quiet, and simple universe, a stark contrast to the seething inferno of its first moments. This period is one of the greatest mysteries in cosmology because it leaves behind almost no direct evidence for us to observe. It is a silent gap in our cosmic story, 100-million-year pause between the flash of creation and the dawn of the first luminous objects. This era was not entirely static, however. Within that immense darkness, the faint seeds of structure planted by the primordial sound waves began to slowly, silently coalesce. The subtle variations in density, those frozen ripples in the cosmic microwave background, meant that some regions of the gas were ever so slightly denser than others. Over millions of years, the relentless pull of gravity worked on these minute fluctuations. The slightly denser patches of hydrogen and helium gas began to attract more and more matter, growing imperceptibly in mass. This was the universe's patient preparation, a slow-motion gathering of material that would eventually become the first stars and the first galaxies. We cannot observe this process directly with our telescopes because there was no light being emitted. It is like trying to study the formation of a snowflake in a pitch-black room. We know the conditions were right for it to happen, but the process itself remains hidden from our view. Understanding this dark age is crucial because it sets the stage for everything that follows. The way in which that primordial gas collapsed, the size of the first structures that formed, and the timing of when the darkness was finally broken, all of these factors would dictate the future architecture of the cosmos. It was during this long night that the potential for stars, planets, and ultimately us was silently, invisibly being written into the fabric of the universe. The end of this era would arrive with a cosmic revolution, a transformation so dramatic that it would rip the very atoms of the universe apart all over again. The profound silence of the cosmic dark age was eventually shattered by an event so colossal it fundamentally rewrote the laws of the nascent universe. The darkness did not recede gently with the appearance of a few faint, sun-like stars. Instead, the first light to emerge was a terrifying, brilliant blaze from celestial giants so immense they defy our modern understanding of what a star can be. These were not stars as we know them today. These were the first generation, known to astronomers as population 3 stars, and their existence is our fourth forgotten fact about the universe's origins. They were true monsters, behemoths that made our own sun look like a tiny, insignificant ember. To comprehend why these first stars were so different, we need to consider the ingredients available. The universe after the Dark Age was a vast, pristine sea of hydrogen and helium gas. There was absolutely nothing else. No carbon, no oxygen, no silicon, no iron. This purity had a dramatic consequence for how stars could form. In today's universe, when a cloud of gas collapses to form a star, it contains trace amounts of these heavier elements which are excellent at radiating away heat. This allows the cloud to fragment into many smaller, denser clumps, leading to the birth of a whole cluster of stars of various sizes, most of them relatively small like our sun. But in the early universe, without these heavy elements to cool the gas, the collapsing hydrogen clouds could not fragment efficiently. They simply collapsed inward in one enormous monolithic cascade, gathering staggering amounts of mass without breaking apart. The result was a star of almost unimaginable scale. While our Sun has a mass of one solar mass, these first stars likely ranged from 100 to over 1,000 times the mass of the Sun. Picture a single star so large that it could contain our entire solar system within its diameter, a sphere of incandescent gas so vast it beggars belief. And because of their tremendous mass, the pressures and temperatures at their cores were exponentially higher than in any star that exists today. They burned not with the steady, efficient fusion of our Sun, but with a ferocious, desperate intensity. They fused hydrogen into helium at a rate that was breathtakingly fast, shining with a brilliance millions of times greater than the Sun. Their light was not the friendly yellow-white we are accustomed to. It was an intense, blistering blue-white or even ultraviolet, flooding the young universe with energetic radiation that began to fundamentally alter the cosmic environment around them. This incredible power came at a cost, a tragically short lifespan. A star like our Sun is a model of stellar longevity, burning steadily for about 10 billion years. But these monstrous first stars lived fast and died young. Their furious consumption of fuel meant they exhausted their core hydrogen in just a few million years, a mere cosmic blink of an eye. Their deaths were as spectacular as their births. The most massive of them did not simply fade away. They ended their lives in titanic supernova explosions of a scale we can scarcely comprehend. These were not ordinary supernovae. For stars above a certain mass threshold, the collapse at the end of their life was so extreme that it might have triggered a phenomenon known as a pair instability supernova. In this cataclysm, the core temperature becomes so high that light itself spontaneously converts into pairs of electrons and positrons. This process robs the core of the pressure supporting it against gravity, leading to a runaway collapse and a thermonuclear explosion so violent that the star is completely obliterated, leaving no black hole or neutron star behind. It is utterly vaporized, its entire contents blasted out into space. This spectacular destruction, however, was the universe's most crucial act of creation up to that point. Within the furnaces of these first stars, and in the unimaginable heat of their supernova deaths, the first heavy elements were forged. Through the process of fusion, these stars cooked hydrogen and helium into heavier elements like carbon, oxygen, and neon. Then, in the final seconds of their supernova explosions, even heavier elements like iron, gold, and uranium were synthesized. The violent death of these first stellar giants scattered these newly forged elements across the cosmos, seeding the pristine hydrogen and helium gas with the first traces of metal. This pollution was the greatest gift imaginable. It enriched the cosmic gas clouds, allowing future generations of stars to form with a richer mix of elements. This, in turn, made it possible for those stars to have planetary systems with rocky planets like Earth, and eventually for the chemistry of life to begin. Every atom of oxygen we breathe, every particle of iron in our blood, and every speck of carbon that forms the basis of our life was forged in the heart of a long-dead star. But the very first of those elements, the ones that started it all, came from these primordial monsters that lived for only a few million years. We are, in a very real sense, the legacy of stars that were too massive to live long, but whose spectacular deaths made our existence possible. But the spectacular lives and deaths of those first stars did more than just forge new elements. They illuminated a cosmos whose very nature was fundamentally different from what we perceive today. This brings us to a fact so central to modern cosmology that getting it wrong completely distorts our understanding of the universe's birth. Fact 5. The Big Bang was not an explosion in space, but an explosion of space itself. This is perhaps the most common and persistent misconception about the origins of everything. We are conditioned by our everyday experience to picture an explosion, a bomb going off at a specific location, hurling debris outward into a pre-existing empty arena. This mental image suggests that if we could travel fast enough, we might reach the edge of the expanding debris field, or even find the central point where it all began. But this picture is fundamentally incorrect, and replacing it is key to grasping the true weirdness of our cosmic origins. The crucial distinction lies in the nature of the arena. In the traditional explosion model, space is the static stage upon which the cosmic drama unfolds. In the Big Bang model, space itself is a dynamic actor in the drama. The event was not matter exploding outward into nothingness. It was the simultaneous expansion of all of space everywhere from a state of incredible density and heat. A powerful analogy to help visualize this is to think of the universe as a loaf of raisin bread dough just before it is baked. The raisins are scattered throughout the dough. Now, as the dough is baked, it begins to rise and expand. Importantly, the raisins are not actively moving through the dough, they are embedded within it. As the dough expands, the space between every raisin increases. From the perspective of any single raisin, it would appear that all other raisins are moving away from it, and the farther away a raisin is, the faster it seems to be receding. There is no center to the expansion within the dough itself. The expansion is a property of the entire loaf. This is exactly how cosmic expansion works. The galaxies are like the raisins, and the fabric of space-time is the dough. The galaxies are not hurtling through space away from a common point of origin. Rather, the space between them is stretching. This explains one of the most profound observations in astronomy. Every distant galaxy cluster appears to be moving away from us, and the most distant ones are receding at speeds approaching the speed of light. It is not that we occupy a special, central location in the universe. An observer in any other galaxy would see exactly the same thing, every other galaxy rushing away from them. The expansion is uniform and happening everywhere at once. This concept also resolves the confusing question of where the Big Bang happened. It did not occur at a single point in space that we could, in theory, point a telescope toward. Instead, it happened everywhere. The entire universe that we see today, across tens of billions of light years, was once compressed into an extremely hot, dense state that occupied every single point. The space between the planets, the stars, and even the atoms in your body was once part of that primordial inferno. As space expanded, it carried the embedded matter and energy along with it, cooling and diluting the cosmos into the vast, structured universe we observe today. This realization forces us to abandon the idea of a center or an edge to the universe. The cosmos might be infinite, or it might be finite but without a boundary, like the surface of an expanding balloon. Trying to find the location of the Big Bang is like asking where on the surface of the Earth the expansion of the Earth's surface began. The question itself is based on a flawed understanding of the geometry involved. Recognizing that space itself is dynamic is the first step toward understanding even more bizarre aspects of our cosmic origins, aspects that challenge the very nature of reality. This concept of space itself stretching, rather than objects flying through it, opens the door to one of the most mind-bending and essential facts about our cosmic beginnings. If we rewind the expansion we see today back to the very first moments, we encounter a logical puzzle so severe that it threatened to undermine the entire Big Bang theory. The puzzle is known as the horizon problem, and its solution requires us to accept a fact that sounds like pure science fiction. For an infinitesimally brief instant, the entire observable universe expanded at a speed far greater than the speed of light. This is our sixth forgotten fact, and it is the cornerstone of the theory known as cosmic inflation. The horizon problem is a puzzle of uniformity. When we look at the cosmic microwave background radiation, the ancient light from when the universe was only 380,000 years old, we see something remarkable. No matter which direction we point our telescopes, the temperature of this afterglow is almost exactly the same, uniform to about 1 part in 100,000. This might not sound strange at first, but consider the implications. In the standard Big Bang model without inflation, the universe had not existed long enough for light or any form of information to have traveled between distant regions. For example, a point on one side of the observable sky and a point on the exact opposite side were so far apart that even traveling at light speed, there would have been no time for them to exchange heat and reach the same temperature. It would be like walking into a large room and finding that every single corner, even those completely isolated from each other, was at precisely 70 degrees Fahrenheit without any prior communication. This level of uniformity should be impossible unless the universe began in a state of perfect, preordained thermal equilibrium, which physicists find highly unlikely. Cosmic inflation provides an elegant and powerful solution. The theory proposes that before the universe underwent the more gradual expansion we see today, it experienced an incredibly brief exponential growth spurt. This period lasted from about 10 to the power of -36 seconds to perhaps 10 to the power of -32 seconds after the beginning. In that almost inconceivably short span of time, a region of space smaller than a single proton was stretched to a size larger than our entire observable universe. Think about that for a moment. A speck of existence smaller than the smallest component of an atom was inflated to a volume encompassing all the hundreds of billions of galaxies we can see and far, far beyond. This is not a matter of things moving quickly through space. It is space itself stretching at a rate that is truly superluminal, faster than the speed of light. And this is where a critical distinction saves the theory from breaking the laws of physics. Einstein's theory of relativity firmly states that no object or information can travel through space faster than light. However, it places no such restriction on the expansion of space itself. There is no cosmic speed limit for the stretching of the fabric of spacetime. A useful analogy is to imagine two ants on a rubber band. The ants can only crawl along the band at a maximum speed, say 1 inch per second. This is like light speed through space. But if you begin to stretch the rubber band itself, the distance between the two ants can increase at a rate much faster than 1 inch per second, even though the ants are not moving relative to the band. The inflation of the universe acted in exactly this way, rapidly pulling regions of space that were once in causal contact far apart from each other. This process of hyper-fast expansion solves the horizon problem beautifully. Before inflation began, the entire seed of our universe was a tiny, subatomic volume. This minuscule region had more than enough time to reach a uniform temperature to homogenize because it was so incredibly small. Then, inflation kicked in, taking this tiny, uniform patch and stretching it to a cosmic scale. What we see as the entire observable universe with its perfectly uniform background temperature is just a small part of that one minuscule pre-inflated region that was smoothed out before the Great Expansion. The distant parts of the sky that appear to have never been in contact were, in fact, neighbors before inflation blew them apart. But the implications of inflation stretch even further into realms that challenge our very definition of reality. If a quantum fluctuation in the early universe could trigger this inflationary expansion in one patch of space, what is to stop it from happening elsewhere? The theory strongly suggests that inflation is not a one-time event that created our single universe. Instead, it may be an eternal process, happening in different places at different times within a much larger, perhaps infinite, meta-reality often called the multiverse. In this picture, our entire cosmos, with all its galaxies, stars, and planets, is just one inflationary bubble in a vast, frothing sea of continuously creating universes. Each of these bubble universes could have different physical constants, different dimensions, and different laws of nature. Some might be stillborn, collapsing instantly. others might expand so rapidly that matter never coalesces. We find ourselves in one where the constants are just right for our existence, a concept known as the anthropic principle. The theory of inflation, born from solving a puzzle of temperature, ultimately suggests that our universe is not the entire story, but merely a single chapter in an infinite book of cosmic genesis. This revelation that our universe may be just one bubble in an endless cosmic foam leads us to a fact that is perhaps the most humbling of all. When we gaze at the night sky with its countless stars and swirling galaxies, we naturally assume that everything we see, every shining point of light, every cosmic cloud represents the totality of the cosmos. But the astonishing truth is that all of that, the entire grand spectacle of the visible universe, is just a tiny fraction of what's actually out there. Fact 7. Most of the universe is made of nothing we understand. The stars, planets, gas, and dust that we can observe, the stuff we are made of, constitutes less than 5% of the universe's total mass energy content. The remaining 95% is composed of two profound mysteries, dark matter and dark energy. Let's start with dark matter, which makes up about 27% of the universe. We've known something was amiss since the 1930s when astronomer Fritz Zwicky was studying the Coma cluster, a massive group of galaxies. He noticed that the individual galaxies within the cluster were moving so quickly that the cluster's gravity, based on the visible mass of all its stars, should not have been strong enough to hold them together. The cluster should have flown apart long ago. It was as if the galaxies were acting like cars on a gravitationally invisible racetrack held in place by some unseen mass. For decades, this was considered a curiosity, but the evidence became undeniable in the 1970s with the work of Vera Rubin. She meticulously measured the rotation speeds of stars within spiral galaxies. According to Newton's laws, stars on the outer edges of a galaxy, far from the central bulge of mass, should orbit much more slowly, just as Pluto orbits the Sun more slowly than Earth does. But Rubin found that stars at the edge of galaxies were orbiting just as fast as those near the center. The only plausible explanation was that each galaxy was embedded within a gigantic, invisible halo of some unknown material, providing the extra gravitational pull to keep the stars from flying off into space. This stuff doesn't emit, absorb, or reflect light, hence the name dark matter. It interacts with normal matter only through gravity. We can map its presence by observing how its immense gravitational field bends the light from distant galaxies, an effect called gravitational lensing, creating ghostly arcs and rings in our telescopes. We are surrounded by it, passing through vast seas of it every second, yet it remains utterly invisible and undetectable by any conventional means. It is the cosmic scaffolding upon which galaxies are built, the hidden architecture that dictated the large-scale structure of our universe from the very beginning. If dark matter is the mysterious glue holding the cosmic structures together, then dark energy is the even more baffling force that is tearing the cosmos apart on the grandest scale. Accounting for a staggering 68% of the universe, dark energy's story begins in the late 1990s. Two independent teams of astronomers were observing distant supernova, using them as cosmic mile markers to measure how the expansion rate of the universe has changed over time. Everyone expected that the gravitational pull of all the matter in the cosmos would be slowing the expansion down, like gravity gradually slowing a ball thrown upward. To their profound shock, the teams discovered the opposite. The expansion is not slowing down at all. It is speeding up. The universe is undergoing accelerated expansion, as if some repulsive force, a kind of anti-gravity, is at work on cosmic scales. This mysterious culprit was dubbed dark energy. What could it be? The leading, yet deeply strange, explanation points back to an idea Albert Einstein once proposed and then discarded: a cosmological constant, an inherent energy woven into the very fabric of empty space itself. According to quantum physics, a perfect vacuum isn't really empty. It's a seething foam of virtual particles popping in and out of existence. This vacuum energy could have a repulsive gravitational effect. The problem is that when physicists try to calculate the predicted strength of this energy, the theoretical value is astronomically, laughably larger than what we observe, off by a factor of 10 to the power of 120. This is often called the worst prediction in the history of physics. It means our understanding of the vacuum is fundamentally incomplete. Another possibility is that dark energy is not a constant but a dynamic field that has changed over time, a concept sometimes called quintessence. Regardless of its true nature, the implication is staggering. Dark energy's dominance means that in the far future, galaxies beyond our own local group will eventually be pushed away by the expansion of space so rapidly that their light will never be able to reach us. The observable universe will shrink, and the cosmos will become a much darker, lonelier place. The fate of the universe appears to be dictated not by the stuff we see, but by the empty space we don't. So, when we look up at the heavens, we are truly seeing only the tip of the iceberg. The glittering stars and majestic galaxies are merely the visible froth on a deep, dark ocean of unknown substances and forces. This composition, 5% familiar atoms, 27% dark matter, and 68% dark energy, is the ultimate census of our cosmos, a recipe that remains almost entirely mysterious. It is a profound reminder that for all our knowledge, we still do not know what 95% of the universe is made of. Our story of cosmic origins is therefore still largely a story of the unknown, a narrative waiting for its next great revelation. And yet, even as we grapple with the invisible 95% of the cosmos, we possess a direct, tangible link back to a time when the universe was anything but dark and empty. This relic is the cosmic microwave background radiation, the oldest light in existence, and it carries within it the precise thermal signature of our universe's fiery infancy. Its temperature today is 2.725 Kelvin, a number that seems almost inconsequentially cold, just a few degrees above the absolute zero of -273.15 degrees Celsius. But this frigid reading is the final, cooled-down whisper of a primeval roar. It is the afterglow of creation itself, stretched and faded by 14 billion years of relentless cosmic expansion. To understand how this light reached us, we must return to that pivotal moment about 380,000 years after the Big Bang. Before this time, the universe was an opaque plasma, a soupy mix of protons, electrons, and light. Photons of light could not travel freely. They were constantly bouncing off or scattering from the dense sea of free electrons like headlights in a thick, impenetrable fog. But as the universe continued to expand and cool, a critical threshold was crossed. The temperature dropped enough for electrons to be captured by protons, forming the first stable, neutral atoms, mostly hydrogen and helium. This process, known as recombination, suddenly cleared the cosmic fog. With the electrons now bound into atoms, the photons were finally set free. They could travel across the universe in straight lines, largely unimpeded for the first time. The light released in that moment was incredibly energetic, shining with a brilliant, white-hot intensity. But as space itself expanded over the ensuing billions of years, it stretched the very wavelength of that ancient light. Imagine drawing a wave on a balloon and then inflating it. The wave would be stretched out, becoming longer and lower in energy. This is exactly what happened to the cosmic microwave background. The once visible and ultraviolet light has been stretched so dramatically by the expansion of the universe that it has been shifted all the way down the electromagnetic spectrum into the microwave region. We perceive it now as a faint, uniform glow that fills the entire sky in every direction. If our eyes could see microwaves, the night sky would not be dark at all. It would be illuminated with a dull, omnipresent glow, the final echo of the Big Bang's flash. The detection of this radiation in 1965 by Arno Penzias and Robert Wilson was a monumental, if somewhat accidental, discovery that earned them a Nobel Prize. They were using a large horn antenna for radio astronomy and kept finding a persistent, annoying background noise that came from every direction and wouldn't go away no matter what they did. After eliminating potential sources like pigeon droppings in the antenna, they realized they had stumbled upon the definitive proof for the hot Big Bang model. They had found the cooled remnant of the primordial fireball, but the true cosmic treasure was not just the uniformity of this background, but the tiny, exquisite imperfections within it. When satellites like the Cosmic Background Explorer, or COBE, mapped the entire sky with exquisite precision in the 1990s, they revealed that the 2.725 Kelvin temperature was not perfectly smooth. There are minuscule variations, tiny ripples of hot and cold, differing by only about 1 part in 100,000. These fluctuations are far from random noise. They are the frozen imprint of the quantum seeds from which the entire cosmic web of galaxies grew. These tiny density variations in the early plasma were the gravitational footholds that dark matter could grip. Over eons, slightly denser regions pulled in more and more matter, eventually collapsing under their own gravity to form the first stars, galaxies, and the vast clusters we see today. The entire grand structure of the modern universe is written in code on this ancient canvas of light. By decoding these subtle temperature differences, cosmologists can read the universe's genetic blueprint, understanding its composition, its shape, and even its ultimate fate from a snapshot taken in its earliest childhood. Yet, as we decode the blueprint of the cosmos from that ancient light, we are forced to confront a possibility even more radical than an expanding vacuum or invisible matter. We take for granted that the laws of physics are immutable, the fixed rules of reality that have governed the universe since the very beginning. The speed of light in a vacuum is always exactly 299,792,458 meters per second. The strength of gravity never wavers. These constants appear to be the bedrock of existence, but what if that bedrock was once more like shifting sand? Our ninth forgotten fact proposes a staggering idea. The fundamental constants of nature may not have been constant at all in the universe's first fleeting moments. This concept challenges our most basic assumptions about reality. The fine-tuning of the universe is one of the greatest mysteries in science. The values of the fundamental constants, like the strength of the electromagnetic force, the mass of an electron, or the cosmological constant, seem almost miraculously precise. If the force that holds atomic nuclei together, the strong nuclear force, were just a few % stronger or weaker, stars might never have formed, or the universe might be composed only of hydrogen. If gravity were slightly stronger, the universe would have collapsed back on itself shortly after the Big Bang. If it were slightly weaker, matter would never have clumped together to form galaxies. The odds of all these constants aligning by random chance to create a life-permitting universe are astronomically small. This has led some scientists to wonder if these values were somehow set, or perhaps even evolved during the extreme conditions of the very early cosmos. One fascinating line of speculation comes from the work of physicists like John Webb, who has analyzed light from incredibly distant quasars. His observations suggest that the fine structure constant, which governs the strength of electromagnetic interactions, might have been slightly different billions of years ago. While this remains a topic of intense debate, it opens the door to the idea that the laws we consider fixed may have undergone a process of settling, like a cooling piece of metal setting into its final shape. In the unimaginable heat and density of the first instance after the Big Bang, the fundamental forces we see as distinct, electromagnetism, the weak nuclear force, the strong nuclear force, and gravity, are thought to have been unified into a single primordial superforce. As the universe expanded and cooled, this superforce underwent a series of symmetry breaks, much like water freezing into ice crystals. where the once unified forces crystallized into the separate interactions we know today. It is during these phase transitions that the constants that define each force could have been determined, perhaps randomly, locking in the values that would dictate the future of cosmic evolution. This is where theories like string theory offer a mind-bending framework. String theory proposes that the fundamental constituents of reality are not point-like particles but tiny, vibrating strings. The way these strings vibrate determines the properties of the particles they manifest, including the apparent values of the physical constants. But string theory often requires more than the three spatial dimensions we experience. It suggests the existence of additional, compactified dimensions, curled up into sizes so small we cannot perceive them. The shape and size of these hidden dimensions would directly influence how the strings vibrate, and thus the laws of physics in our observable universe. In this view, the constants are not fundamental, but are rather the local byproduct of the specific geometric configuration of these extra dimensions in our particular patch of the cosmos. A different configuration would yield a completely different set of physical laws. This idea dovetails powerfully with the concept of the multiverse arising from eternal inflation. If inflation continuously spawns countless bubble universes, and if the physical constants in each bubble are determined by random processes or by different compactifications of extra dimensions, then our universe is not fine-tuned. It is simply one among a near-infinite ensemble where, by sheer chance, the numbers came out right for life to emerge. We find ourselves in a hospitable universe for the same reason a fish finds itself in water. It is the only kind of place where beings like us could possibly exist to ponder the question. This anthropic reasoning offers a potential explanation for fine-tuning without requiring a designer, but it replaces one mystery with another, the existence of an unfathomably vast multiverse forever beyond our observational reach. Whether the constants were set randomly, evolved dynamically, or are truly immutable, their precise values remain a profound puzzle at the heart of our cosmic origin story, a silent testament to the deep and mysterious order underlying all of reality. But if the laws of physics themselves were once in flux, it forces us to confront the ultimate question: what, if anything, came before the beginning? We have been tracing the history of our universe back to a singular moment of infinite density and temperature, a point where our current laws of physics simply break down. This singularity seems like an absolute barrier, a definitive start to time and space. However, some of the most compelling theories in modern cosmology suggest that this barrier is not a wall but a gateway. Fact 10. There might have been a universe before the Big Bang. The idea of a true beginning may be an illusion, replaced by the grander concept of an eternal cycle of cosmic death and rebirth. One of the most elegant of these cyclical models is known as the Big Bounce. Instead of a universe emerging from a singularity, this theory proposes that our expanding cosmos was preceded by a contracting one. Picture a previous universe, perhaps very similar to our own, but one that had exhausted its capacity for expansion. Over trillions of years, dark energy's push weakens or reverses, and the relentless pull of gravity takes over. Galaxies begin to draw closer together, then clusters, until the entire universe starts to collapse in on itself in an event nicknamed the Big Crunch. Everything, stars, planets, space itself, is compressed into an unimaginably hot, dense state. But according to the Big Bounce scenario, this compression does not end in a singularity. Instead, quantum gravitational effects, phenomena we don't yet fully understand but are predicted by theories like loop quantum gravity, become dominant. These effects generate a powerful repulsive force, turning the collapse around into a new expansion. The Big Crunch becomes the Big Bang for a new cosmic cycle. In this view, our universe is just the latest incarnation in an endless series of expansions and contractions, a cosmic phoenix forever rising from its own ashes. An even more radical and poetic vision comes from Nobel laureate Sir Roger Penrose, called conformal cyclic cosmology, or CCC. Penrose's theory sidesteps the need for a bounce altogether by focusing on a strange symmetry that emerges at the very end and the very beginning of time. In the far, far future, trillions upon trillions of years from now, the universe will be a cold, dark, and empty place. All stars will have burned out, all black holes will have evaporated through Hawking radiation, and all matter will have decayed into its most basic particles. In this state of maximum entropy, the universe becomes incredibly large, empty, and simple. There are no clocks to measure time and no rulers to measure distance because there are no significant mass differences or events to create a scale. The universe, in a mathematical sense, loses its sense of scale. It becomes conformally invariant. Astonishingly, this state of vast, cold nothingness is mathematically identical to the hot, dense, and simple state of the Big Bang singularity. Penrose proposes that these two states are, in fact, the same. The remote future of one universe becomes the hot Big Bang of the next. In this model, the universe has no beginning and no end, only an infinite series of eons, each starting with a Big Bang and ending in a featureless void that seamlessly transforms into the next Big Bang. Penrose even suggests that evidence for this might be found in the cosmic microwave background, in the form of faint, concentric circles which he calls Hawking points, potentially imprints of gravitational radiation from supermassive black holes that collided in the previous eon. Then there is the mind-bending possibility arising from string theory, the brain-world scenario. Imagine our entire three-dimensional universe is not all there is, but is simply a three-dimensional membrane, or brain, floating within a higher dimensional space called the bulk. Other brains, representing other universes with different physical laws, could be floating in this bulk alongside ours. In this picture, our Big Bang might not have been an internal event at all, but the result of a colossal collision between our brain and a neighboring one. The immense energy of such a collision would have been concentrated into our three-dimensional space, heating it to an incredible temperature and initiating the expansion we observe. This is not a cyclical model in the traditional sense, but it still suggests an eternal, pre-existing reality. The brains could be oscillating through the bulk, periodically colliding and moving apart, with each collision creating a new hot Big Bang in each of the participating universes. Our entire cosmic history would just be one episode in an endless higher dimensional dance. These ideas profoundly challenge the very meaning of before. If time as we know it began with our Big Bang, then talking about a before is linguistically and physically problematic. However, in models like the Big Bounce or the cyclic eons of conformal cyclic cosmology, the timeline is continuous. The before refers to a previous phase of a grander meta-time that encompasses all cycles. In the brain-world scenario, the before exists in the higher dimensional bulk, where time may flow independently of the time within our brain. While these theories are still speculative and lie at the frontiers of theoretical physics, they represent a monumental shift in perspective. They replace the mystery of a single, uncaused beginning with the equally profound mystery of an eternal, perhaps infinite, existence. The quest to understand our origins may ultimately reveal that the universe has always been, and will always be, in a state of endless, magnificent transformation. Yet from these grand cycles and cosmic collisions, the universe we know was built upon a foundation of astonishing simplicity. After the formation of the first atoms, the cosmos was a vast, expanding sea of hydrogen and helium nuclei, along with a sea of free electrons. But for the great gravitational collapse that would birth the first stars to begin, this primordial gas needed a way to cool down. Heat generates pressure which fights against gravity's pull. For a cloud of gas to collapse into a star, it must be able to shed energy to shrink and become denser. And this required a crucial yet often overlooked step, the birth of the very first molecule. This leads us to fact 11. The first molecules were surprisingly simple, yet their formation was absolutely crucial for lighting up the cosmos. For chemistry to begin, single atoms needed to find a way to link together. But in the early universe, this was a tremendous challenge. The environment was still flooded with the intense energy of the cosmic microwave background radiation, and high-energy photons are very effective at breaking apart fledgling chemical bonds. Furthermore, the most abundant atom, hydrogen, exists as a single proton and a single electron. Two hydrogen atoms attempting to form a molecule known as molecular hydrogen or H2 face a problem. The process is relatively inefficient. It often requires a third body to carry away excess energy for the bond to stabilize, which was unlikely in the diffuse early gas. Without an efficient pathway to form cooling molecules, the universe might have remained a dark, sterile expanse of slowly drifting atoms. The solution arrived in the form of a seemingly insignificant union, the helium hydride ion, written as He+. This was the very first molecular bond ever to form in the universe. Its creation was a two-step dance of fundamental particles. First, a neutral helium atom with its 2 protons and 2 electrons encountered a free proton, which is essentially a hydrogen nucleus. The helium atom, with its stable, closed electron shell, is generally inert and doesn't like to react. However, in the dense, energetic conditions of the early universe, the proton could sometimes get close enough to polarize the helium atom, distorting its electron cloud just enough to form a weak but real bond. This created the helium hydride ion, a positively charged molecule consisting of a helium atom and a proton sharing a connection. While fragile, the helium hydride ion played an outsized role as a cosmic catalyst. Its importance lay in its chemistry. When a helium hydride ion collided with a neutral hydrogen atom, a proton transfer could occur. The hydrogen atom, eager to have its own electron, would essentially steal the proton from the helium hydride ion. The reaction would look like this: He++H, He plus H2+. This produced a molecule ion of hydrogen, H2+, and freed the helium atom. This hydrogen molecule ion could then react with another neutral hydrogen atom, forming stable molecular hydrogen, H2++ H2+ H+. This two-step process, initiated by the helium hydride ion, provided a much more efficient pathway for creating molecular hydrogen than 2 hydrogen atoms trying to link up directly. And molecular hydrogen was the key that unlocked the universe. Unlike single atoms, which can only cool by radiating light in specific, narrow wavelengths when their electrons jump between energy levels, molecules have a more versatile cooling mechanism. They can rotate and vibrate, emitting infrared radiation across a much broader range of frequencies. Molecular hydrogen acted as a universal radiator for the primordial gas clouds. As these clouds began to contract under gravity, the H2 molecules inside them converted the gravitational energy into vibrational and rotational energy, which was then radiated away as infrared light. This allowed the clouds to lose heat, reduce their internal pressure, and continue collapsing into ever denser clumps. Without this efficient cooling provided by molecular hydrogen, the gas would have remained too hot and diffuse, and the gravitational collapse that formed the very first stars would have been impossibly slow or might never have happened at all. The humble helium hydride ion, therefore, was the essential spark for cosmic chemistry, the missing link that allowed the simple atomic soup to transition into a universe capable of building the complex structures of stars and galaxies. For decades, helium hydride remained a theoretical prediction, a ghost from the dawn of time that had never been observed in space. Then, in 2019, astronomers using the Sophia Airborne Observatory detected its faint signature in a planetary nebula, finally confirming its existence and providing a tangible connection to the chemical processes that ignited the cosmic dark age. The destiny of our cosmos, whether it will expand into an endless cold void or ultimately collapse back into a fiery singularity, was not a question that would take billions of years to answer. In fact, the verdict was delivered in the universe's very first second of existence. This fate was sealed by a delicate and dramatic balancing act between two opposing forces: the outward momentum of the initial expansion and the inward pull of all the matter and energy contained within the universe. Cosmologists describe this balance with a single, crucial number known as omega, the density parameter. If you could have taken a cosmic measuring tape in that first fraction of a second, the value of omega would have told you everything about how the story would end. Imagine omega as a cosmic scale. On one side of the scale, you have the kinetic energy of the Big Bang, the sheer explosive force that was hurling space-time apart. On the other side, you have the total gravitational pull of all the mass energy in the universe, trying to halt and reverse that expansion. The outcome hinges entirely on which side is heavier. If the density of the universe was very high, meaning omega was greater than 1, gravity would eventually win. The expansion would slow, stop, and then reverse in a catastrophic big crunch, pulling all of existence back into a singularity. This is known as a closed universe with a geometry analogous to the surface of a sphere, a finite but without an edge. Conversely, if the density was too low with omega less than 1, gravity would be too weak to ever reign in the expansion. The universe would expand forever, cooling into a vast, dark, and dilute emptiness. This is an open universe with a geometry like a saddle, curved negatively and extending infinitely. But there is a third, razor-sharp possibility, the critical density. This is the precise knife-edge balance where omega equals exactly 1. In this scenario, the expansion rate and the gravitational pull are perfectly matched. The universe would continue to expand forever, but its speed would asymptotically approach zero, never quite stopping but getting infinitely close. This defines a flat universe where the rules of Euclidean geometry we learned in school, like parallel lines never meeting, hold true on the largest scales. For decades, determining which of these fates was ours was one of the primary goals of cosmology. The answer seemed to lie in patiently measuring the total amount of matter in the cosmos, a painstaking task that involved counting galaxies and estimating the hidden mass of dark matter. The stunning revelation, confirmed with high precision by satellites like the Wilkinson Microwave Anisotropy Probe and the Planck spacecraft, is that our universe is flat. The measurements of the cosmic microwave background's subtle fluctuations show that omega, for the total mass energy content, is extraordinarily close to 1. This seems to solve the mystery. We live in a flat universe, so its expansion will continue forever, gradually slowing toward a halt. But this is where the plot thickens and dark energy re-enters the narrative. The discovery of the accelerating expansion in the late 1990s added a profound twist. While the universe is geometrically flat, meaning its fate was determined by that initial critical density, the presence of dark energy has overridden the simple expansion slowing scenario. Instead of coasting to a near stop, the universe is now accelerating away. So, the initial condition of flatness set the stage, but dark energy has written a new, unexpected ending to the play, one of perpetual and increasingly rapid expansion into an ever lonelier future. The vast, flat geometry of our universe, set in its first second, provided the pristine stage. The formation of the first molecules provided the essential coolant. But what provided the script? What determined where the first stars would ignite and the first galaxies would coalesce? The answer lies in a concept that bridges the unimaginably small and the cosmically vast. Our 13th forgotten fact reveals that the blueprint for everything, every galaxy, every star, every planet was written by the ghostly hand of quantum randomness. The largest structures in the cosmos owe their existence to the tiniest of tremors in the fabric of reality at the very beginning of time. To grasp this, we must shrink our perspective down to the quantum realm. In the world of particle physics, what we perceive as empty space is not truly empty. It is a seething, bubbling foam of energy. Due to the Heisenberg uncertainty principle, it is impossible to have a state of exactly zero energy for a precisely defined period. This leads to a remarkable phenomenon. Virtual particle-antiparticle pairs constantly pop into existence out of nothingness, borrowing energy from the vacuum for an infinitesimally short time before annihilating each other and vanishing back into the void. These are quantum fluctuations, fleeting ripples in the energy fields that fill the universe. In our everyday world, these fluctuations are utterly negligible, their effects far too small to notice. But now, let's rewind to the period of cosmic inflation. Remember that brief moment when a subatomic speck of space was inflated to a size larger than our observable universe. During that hyper-fast expansion, something extraordinary happened to those tiny quantum fluctuations. As space stretched at a rate faster than light, it did not simply enlarge the universe, it also stretched the very fabric of those quantum ripples. A microscopic fluctuation that was once smaller than a proton was suddenly blown up to a macroscopic scale. The random, ghostly flicker in an energy field became a real, lasting variation in the density of the universe. Where a fluctuation created a slightly higher concentration of energy, that region became ever so slightly denser than its surroundings. Where it created a slightly lower concentration, a region became a bit emptier. Inflation took the quantum whisper and amplified it into a cosmic shout, imprinting these minute density differences across the entire sky. This process transformed the universe from a featureless, homogeneous soup into a canvas with subtle texture. The once uniform plasma now had a specific pattern of over-dense and under-dense regions. These imperfections were tiny variations of only about 1 part in 100,000, but they were absolutely crucial. They were the gravitational seeds for all future structure. After inflation ended and the universe continued its more sedate expansion, gravity began its patient work. Over millions of years, the slightly denser patches exerted a stronger gravitational pull, slowly attracting more and more matter from their surroundings. Dark matter, which interacts only through gravity, was the first to respond, forming vast, invisible halos. These halos then acted as gravitational wells, pulling in the normal atomic matter, the hydrogen and helium gas. As these gas clouds collapsed into the dark matter scaffolds, they fragmented and condensed, eventually igniting as the first stars and gathering into the first galaxies. The largest overdensities grew into immense galaxy clusters, while the smaller ones became individual galaxies. The underdense regions, meanwhile, evolved into the vast cosmic voids we see today, great empty deserts separating the glittering filaments of the cosmic web. The entire grand architecture of the modern universe, a web of galaxies stretching across billions of light years, is therefore a direct magnified consequence of those quantum fluctuations. The random dice roll at the quantum scale was inflated to a cosmic scale, and gravity did the rest of the work, sculpting the primordial noise into the organized structures we observe. This connection is not just theoretical, we can see its fingerprint with stunning clarity. The pattern of hot and cold spots in the cosmic microwave background radiation is a direct map of those initial density fluctuations. When scientists analyze this pattern, they find that it matches the predictions of quantum mechanics and inflation with remarkable precision. The statistics of the temperature variations are exactly what you would expect if they originated from quantum fluctuations that were stretched across the sky. This is one of the most profound revelations in all of science. The rules that govern the behavior of atoms and subatomic particles are responsible for the distribution of galaxies. The quantum world and the cosmic world are not separate domains. They are inextricably linked, with the birth of the universe serving as the bridge between them. It means that the ultimate origin of the galaxy we call home, the star we orbit, and the planet we live on, can be traced back to a random quantum event in the first fleeting moments of everything. Our existence is, in a very real sense, a consequence of a primordial uncertainty, a fluctuation that grew into a universe. This exploration of quantum seeds leads us to one of the most fundamental and brain-twisting facts of all. The very arrow of time, the steady flow from past to present to future that we experience every moment of our lives, may itself be a product of the Big Bang. We naturally assume that time is an infinite river, flowing eternally from an endless past toward an endless future. But our best understanding of physics suggests something far more radical. Fact 14. Time itself may have had a definitive beginning. To grasp this, we need to look at how Einstein's theory of general relativity describes the universe. In this framework, space and time are not separate, static backdrops against which events unfold. Instead, they are woven together into a single, dynamic fabric called spacetime. Matter and energy tell spacetime how to curve, and the curvature of spacetime, in turn, tells matter how to move. This interconnectedness is crucial. If space expanded from an incredibly dense state, as the Big Bang describes, then time was inextricably linked to that expansion. As we run the cosmic film backwards in our equations, watching the universe contract, we see space shrinking and the density and temperature rising toward infinity. This is the singularity, a point where the curvature of spacetime becomes infinite and the laws of physics, as we know them, simply cease to be valid. At this singularity, the concept of time breaks down completely. It's not just that we don't know what happened, it's that the words before and after lose all meaning. Asking what happened before the Big Bang may be as logically incoherent as asking what is north of the North Pole. The North Pole is defined as the northernmost point on Earth. There is no direction north of it because the concept of north ceases to apply. Similarly, if the Big Bang singularity represents the beginning of time itself, then there is no before because time did not exist. There was no then for anything to happen in. This idea of an absolute beginning has profound philosophical implications. For centuries, philosophers and scientists have grappled with the problem of infinite regress. If the universe has always existed, what set it in motion? If it was created, what created the creator? The standard Big Bang model, by suggesting a beginning for time, offers a way out of this loop. It points to a moment of creation that is not an event in time, but the very genesis of time. The universe would not simply be very old, it would have a finite age because time itself started ticking 14 billion years ago. However, this is not the final word. While the classical theory of general relativity predicts a singularity, we know it is incomplete because it doesn't incorporate the rules of quantum mechanics. Quantum physics, which governs the world of the very small, is built on probability and uncertainty. Physicists suspect that a future theory of quantum gravity, perhaps string theory or loop quantum gravity, will eliminate the singularity. In these models, the universe might have undergone a big bounce from a prior contracting phase, or it may exist as a four-dimensional membrane in a higher dimensional reality where time has always flowed. In these scenarios, our Big Bang is not an absolute beginning but a transition from a previous state of existence. Yet, even in these models, the nature of before remains deeply strange, potentially referring to a different kind of time or a different physical realm entirely. Whether time had a true starting point or is part of an eternal cycle, the Big Bang marks the moment our local arrow of time, our cosmic history as we know it, began its irrevocable forward march. But if the quantum seeds for our cosmos were sown in that first fleeting instant, the physical state of the universe that immediately followed was unlike anything that exists today. Just moments after the beginning, the fundamental ingredients of matter as we know them had not yet taken their familiar forms. To find fact 15, we must travel back to a time before protons and neutrons even existed, to an era when the universe was a searing, exotic substance known as a quark-gluon plasma, a state of matter that behaved as a nearly perfect fluid. We are familiar with the three common states of matter: solid, liquid, and gas. But under conditions of extreme temperature and density, matter transforms into more exotic phases. In our modern, cool universe, the quarks that make up protons and neutrons are perpetually confined. The strong nuclear force, mediated by particles called gluons, binds them together so powerfully that no quark has ever been observed in isolation. They are forever locked inside protons, neutrons, and other particles. This is a fundamental rule of nature as we experience it, but if we rewind the cosmic clock to about 1/1,000,000th of a second after the Big Bang, we encounter a reality where this rule was temporarily suspended. At that time, the entire universe was an unimaginably hot and dense soup, with temperatures exceeding several trillion degrees Celsius. The energy density was so intense that it overwhelmed the powerful force that normally confines quarks. Protons and neutrons could not hold together. Instead, quarks and gluons roamed freely, creating a new state of matter, the quark-gluon plasma. Think of it as a cosmic analog to what happens when you heat an ice cube. The solid ice, like a proton, melts into liquid water, the free quarks and gluons. In this primordial plasma, the universe was not filled with recognizable atoms or even atomic nuclei. It was a churning, super-hot sea of the most fundamental constituents of matter, all interacting freely. One of the most surprising discoveries about this state is how it behaved. Initially, scientists theorized that a quark-gluon plasma would behave like a gas, with particles moving independently and chaotically. However, experiments at powerful particle colliders like the relativistic heavy ion collider in the United States and the Large Hadron Collider in Europe have revealed something far more intriguing. By smashing heavy atomic nuclei like gold or lead together at velocities approaching the speed of light, physicists can recreate, for a microscopic fraction of a second in a volume smaller than an atom, the extreme temperatures and densities of the early universe. In these fleeting fireballs, a quark-gluon plasma is born, and when they study the aftermath of these collisions, they find that this primordial soup does not act like a gas. Instead, it flows with remarkably little internal friction, behaving as a nearly perfect fluid. In physics, viscosity is a measure of a fluid's resistance to flow. Honey, for example, has high viscosity, it flows sluggishly. Water has lower viscosity, it flows more easily. A perfect fluid has zero viscosity, meaning it flows without any resistance whatsoever. The quark-gluon plasma created in these experiments comes astonishingly close to this ideal. It has the lowest viscosity of any known substance in nature. This discovery was a major shock to physicists. It indicates that the constituents of this plasma, the free quarks and gluons, are still strongly coupled to one another, interacting so frequently and intensely that they move in a coordinated, collective manner, much like a school of fish or a crowd of people, rather than as a disorganized gas. This property of near-perfect fluidity tells us something profound about the nature of the strong force and the conditions of the infant universe. In those first microseconds, the cosmos was not a chaotic, disconnected gas. It was a unified, coherent liquid of unimaginable energy. This perfect fluidity allowed pressure waves like the primordial sound waves we discussed earlier to propagate efficiently, helping to shape the density fluctuations that would later seed galaxies. As the universe continued to expand and cool, it crossed a critical threshold. The temperature dropped enough for the strong force to finally overcome the immense thermal energy, and quarks and gluons became confined, coalescing to form the first protons and neutrons. This phase transition, known as hadronization, marked the moment the building blocks of our familiar world snapped into place, freezing out of the seething plasma from which they emerged. By recreating this primordial fluid in the laboratory, we are not just studying particle physics. We are performing experimental archaeology on the first moments of existence, directly probing the liquid fire from which all tangible matter was forged. While we can recreate the quark-gluon plasma in particle colliders, there is another, even more elusive relic from the universe's first second that permeates every corner of space, including the room you are in right now. This brings us to fact 16. The cosmos is flooded with a sea of ghostly particles known as the cosmic neutrino background. If the cosmic microwave background is the ancient photograph of the universe's infancy, this neutrino background is the snapshot from its very first breath, a whisper from a time when the cosmos was barely a second old. To understand their origin, we need to rewind to just 1 second after the Big Bang. At this incredibly early stage, the universe was still an unimaginably dense and hot furnace, far too hot for atoms or even atomic nuclei to exist stably. But it had cooled just enough for a pivotal event to occur. In the first fraction of a second, the universe was so energetic that it was filled with a dense soup of particles and their antimatter counterparts, constantly colliding and annihilating each other in a frenzied dance. Among these were neutrinos, extremely lightweight, neutral particles that interact only via the weak nuclear force and gravity. For a brief window, these neutrinos were in constant thermal equilibrium with the rest of the cosmic plasma, frequently interacting with protons, electrons, and other particles. Then, at the 1 second mark, the universe expanded and cooled past a critical threshold. The energy of the particles dropped to a point where neutrinos could no longer easily interact with matter. They effectively decoupled, meaning they stopped colliding with other particles and began streaming freely across the expanding universe, much like the photons of the CMB would do hundreds of thousands of years later. This moment created a fossil record, a background sea of these primordial neutrinos that has been flowing uninterrupted for nearly 14 billion years. These are not the neutrinos produced by the sun or in supernova explosions today. These are the original ones, the eldest ghosts from the dawn of time. The sheer number of these particles is staggering. For every proton in the universe, there are about 1 billion of these primordial neutrinos. This means that right now, as you watch this, trillions of them are passing through your body every second, completely unnoticed. They are so ethereal that they can traverse light years of solid lead without a single interaction. This ghostly nature is what makes them so fascinating and so maddeningly difficult to study. While we have built gigantic, ultra-sensitive detectors deep underground to catch the rare neutrino from the sun or a distant cosmic event, detecting a neutrino from the Big Bang itself is a challenge of an entirely different magnitude. Their incredibly low energy, cooled by the expansion of the universe to just a tiny fraction of a degree above absolute zero, means they slip through our detectors and even through our entire planet as if it weren't even there. Yet, the information they carry is priceless. Because they decoupled just 1 second after the beginning, they hold secrets about conditions in the universe that the cosmic microwave background simply cannot. The CMB shows us the universe at 380,000 years old, which is like seeing a photograph of a person as a fully grown adult. The cosmic neutrino background, by contrast, is like an ultrasound image from the first day of pregnancy. These neutrinos could tell us about the exact conditions during Big Bang nucleosynthesis, the process that forged the first light elements. They could provide crucial clues about the total number of neutrino species, and perhaps even hint at new, undiscovered types of particles. Detecting them directly remains one of the ultimate frontiers in cosmology, a goal that would open a window into the universe's very first second, a realm currently accessible only through theoretical equations. Looking out at the vibrant tapestry of the night sky with its brilliant blue-white stars, glowing red nebulae, and the delicate hues of planetary systems, it's easy to assume the cosmos has always been this colorful. But the universe of today is a far cry from its original state. In its earliest epochs, the cosmos was visually and chemically monochrome. Fact 17 reveals a profound transformation. The universe's very color has evolved over time, a change driven by the slow alchemical cooking of stars, a process astronomers call increasing metallicity. To grasp this, we need to understand what astronomers mean by metal. In everyday language, we think of iron, gold, and aluminum. But in the language of cosmology, a metal is any element heavier than helium. This is a crucial definition because hydrogen and helium were the only two elements produced in significant quantities during the Big Bang. For the first few 100 million years, the universe was a starkly simple place, composed of about 75% hydrogen and 25% helium by mass. There was no carbon for life, no oxygen for water, no silicon for rock, and no iron for planetary cores. The cosmic palette was limited to just two primordial shades. If you could have observed the first stars and galaxies with a spectrometer, their light would have shown a complete absence of these heavy element signatures. They were metal-free, or in astronomical terms, they had extremely low metallicity. The universe was, in a chemical sense, colorless. The injection of color into this monochrome cosmos began with the dramatic lives and deaths of the first generation of stars. As we've discussed, these massive stars acted as the universe's first nuclear forges. Deep within their cores, under immense pressure and temperature, they began fusing hydrogen into helium. But for the most massive stars, the fusion process didn't stop there. Once the hydrogen in the core was exhausted, the star would contract, heating up further until it could begin fusing helium into carbon. Then, in a layered onion-like structure, it would fuse carbon into heavier elements like oxygen, neon, and magnesium, and so on, all the way up to iron. The formation of elements heavier than iron, however, requires an even more violent process. Iron fusion does not release energy, it consumes it. So when a massive star's core becomes iron, it can no longer support itself against gravity. The core collapses catastrophically in a supernova explosion, and in the unimaginable fury of that blast, the remaining elements are forged, everything from cobalt and nickel to gold, silver, and uranium. Each supernova then acts as a cosmic spray can, ejecting these newly forged metals out into the surrounding interstellar gas. This gas, now enriched with a sprinkling of heavy elements, cools more efficiently and collapses to form a new generation of stars. This second generation of stars is born with a higher initial metallicity. They themselves will fuse hydrogen into helium, but they also contain the seeds of their predecessors, allowing for more complex chemistry in their planetary systems, should they form. When these stars die, often in their own supernova, they pollute the interstellar medium even further, increasing the metallicity for the next generation. This is a progressive cycle of stellar life, death, and rebirth. With each cycle, the galactic gas clouds become richer in heavy elements, and the stars that form from them carry a more complex chemical signature. The universe was slowly painting with a broader and broader palette. Our own solar system is a direct product of this enrichment process. When the Sun formed about 4.6 billion years ago, it did so from a cloud of gas that had been seeded by the remains of many previous generations of stars. The evidence for this is all around us. The rocky planets like Earth are made almost entirely of metals in the astronomical sense: silicon, oxygen, iron, magnesium, and aluminum. The very iron in your blood and the calcium in your bones were forged in the heart of a long-dead star that exploded billions of years before the Sun was born. Our solar system is not a first-generation system. It is a relative latecomer, a product of cosmic recycling that required roughly 8 to 9 billion years of stellar evolution to accumulate the necessary ingredients for planets and life. We are quite literally the children of stars that lived and died long ago, their essence scattered across the galaxy to eventually coalesce into our world. This evolving color of the universe, from the simple primaries of hydrogen and helium to the rich, complex spectrum we see today, is the direct result of stars acting as the universe's great artists, gradually filling the cosmic canvas with the colors of complexity. This grand evolutionary process, driven by the life and death of stars, has fundamentally reshaped the cosmos's chemical identity. But what about the fundamental laws that govern these stellar forges and the very expansion of space itself? The rules seem fixed and eternal, yet our next fact suggests that in the universe's first moments, the rulebook was being written in real time. The four forces we take for granted today were not always distinct entities. In the extreme energy of the very beginning, they were likely melded into a single, unified superforce, and gravity was the most enigmatic player in this cosmic drama. The first to branch off on its own, yet the last to become the dominant architect of large-scale structure. To understand this, we need to explore the concept of symmetry breaking. Think of it like water. At high temperatures, water is a liquid. Its molecules are free to move in every direction, and it possesses a high degree of symmetry. It looks the same from any angle. But when you cool water below 0 degrees Celsius, it undergoes a phase transition and freezes into ice crystals. In doing so, it loses some of that symmetry. The ice crystal has a specific, oriented structure. It picks a preferred alignment. The underlying laws of physics haven't changed, but the system has settled into a new, less symmetric state. A similar process is thought to have occurred as the hot, dense early universe expanded and cooled. The incredible thermal energy of the first fraction of a second kept the fundamental forces in a state of perfect symmetry, unified as one. Physicists believe that as we rewind time toward the Big Bang, the energy scales become so high that the distinctions between the forces blur and then vanish. At these energies, the electromagnetic force and the weak nuclear force, which are separate in our everyday world, unify into a single electroweak force. At even higher energies, approaching the Planck scale, it is theorized that the strong nuclear force and the electroweak force merge into a grand unified force. And at the ultimate energy of the singularity itself, even gravity, the most stubbornly independent force, would have been unified with the others in a state of perfect symmetry. This was the era of the superforce. Then, in the first unimaginably brief instance, as the universe expanded and its temperature plummeted, a series of cosmic phase transitions occurred. With each drop in energy, a force froze out or crystallized from the unified whole, much like ice forming from water. Gravity is thought to have been the first to separate. Why? Because gravity is intimately tied to the very fabric of space-time, and as the universe began to rapidly expand and cool from the Planck scale, the geometry of space-time itself underwent a radical change, causing gravity to decouple. Next, as the energy dropped further, the strong nuclear force broke away from the electroweak force in what is called the Grand Unification Epoch. Finally, when the universe was about a trillionth of a second old, the electroweak force split into the electromagnetic force and the weak nuclear force that we recognize today. This sequence creates a fascinating paradox. Gravity was the first force to gain its independence, yet for most of cosmic history, it has been the weakest force by an almost incomprehensible margin. The electromagnetic force between two electrons is about 10 to the power of 42 times stronger than the gravitational force between them. On the small scale of atoms and molecules, gravity is utterly negligible. So, if it was the first to appear, why did it take so long to become the master of the cosmos? The answer lies in its nature and the conditions of the early universe. Gravity's influence is cumulative and always attractive. It doesn't have positive and negative charges that can cancel out. But in the universe's first moments, everything was so hot, dense, and energetic that other forces dominated. The intense radiation pressure from photons and the furious motion of particles overwhelmed gravity's gentle, persistent pull. It was only as the universe continued to expand, cool, and become more diffuse that gravity's patience became its strength. While the other forces act over short ranges or can be cancelled out, gravity simply kept pulling, acting across the vastness of space. It worked slowly and silently on the tiny quantum fluctuations imprinted by inflation. gradually amplifying them over millions and billions of years. It was gravity that gathered the primordial gas into the first stars. It is gravity that holds galaxies and galaxy clusters together. And on the very largest scales, it is the battle between gravity and the momentum of the Big Bang, now aided by the mysterious push of dark energy that determines the ultimate fate of the cosmos. So, while gravity was the first force to step onto the stage, it waited in the wings for eons, its subtle power growing until it could finally step into the spotlight and begin sculpting the universe we see today. Its delayed dominance is a testament to the fact that in the cosmos, the most profound changes often begin with the quietest, most persistent forces. But if the grand structure we see is the result of gravity patiently sculpting quantum seeds, what is the overall character of the cosmic landscape it has created? When we gaze at a detailed map of the nearby universe, we see anything but uniformity. We find dense clusters of galaxies, vast empty voids, and long, filamentary structures that weave everything together into a great cosmic web. It looks messy, chaotic, and decidedly lumpy. This local reality, however, hides a far grander and more profound truth about the cosmos as a whole. Our 19th forgotten fact reveals that on the very largest scales, the universe possesses a remarkable simplicity and order. It is both isotropic and homogeneous, a finding so fundamental that it forms the bedrock of modern cosmology, known as the cosmological principle. Let's break down what these two terms really mean, because they describe the universe's personality in a profound way. Isotropic means that the universe looks the same in every direction you look. No matter where you point your telescope from any vantage point in the cosmos, the large-scale view is identical. There is no preferred direction, no cosmic north or south, no special axis. Homogeneous means that matter is distributed evenly when you take a big enough sample. While your immediate neighborhood might have a galaxy here and an empty void there, if you zoom out far enough, to scales of hundreds of millions of light years, the average density of matter smooths out to be the same everywhere. Think of it like the foam on a cappuccino. Up close, you see bubbles of all different sizes and shapes with plenty of empty space between them. But if you step back and look at the entire cup from a distance, the foam appears as a uniform, creamy layer. The universe operates on a similar principle. Its lumpiness is a local phenomenon that vanishes when we adopt a truly cosmic perspective. The evidence for this startling uniformity is overwhelming and comes from two powerful lines of observation. The first is the cosmic microwave background radiation. When we map the entire sky, the temperature of this ancient afterglow is uniform to an astonishing degree of precision, about 1 part in 100,000. The minute variations we see are incredibly small ripples on an otherwise perfectly smooth pond. This tells us that when the universe was only 380,000 years old, it was incredibly homogeneous and isotropic. The seeds for future structure were there, but they were tiny imperfections in an otherwise featureless cosmos. The second line of evidence comes from massive galaxy redshift surveys like the Sloan Digital Sky Survey. These projects have meticulously mapped the three-dimensional positions of millions of galaxies. When you analyze these maps, you find that on scales larger than about 500 million light-years, the distribution of galaxies does indeed become smooth. The clustering and voids we see are like waves on the surface of an ocean. From a high enough vantage point, the ocean's surface appears flat and uniform. This cosmological principle is not just an interesting observation. It is a foundational assumption that makes modern cosmology possible. It allows us to apply the same physical laws everywhere and to extrapolate what we see in our local cosmic neighborhood to the universe as a whole. Without this principle, we would be plagued by a kind of cosmic paranoia. We would have to wonder if the physical constants are the same in a distant galaxy cluster, or if the laws of physics themselves vary from place to place. The cosmological principle gives us the confidence to believe that our corner of the universe is not special or unique, a concept sometimes called the principle of mediocrity. We are not at the center of things, we are typical observers in a vast, uniform cosmos. This idea is a profound departure from humanity's historical view of the universe. For centuries, we placed ourselves at the center of creation. The Earth was the midpoint of the cosmos, with everything else revolving around it. Even after the Copernican revolution displaced us from the spatial center, a subtle bias remained. The feeling that we must still be in a somehow privileged location. The cosmological principle completely dismantles this notion. It states that there is no center. Every point in the universe, every galaxy, every potential observer would see the same large-scale picture, galaxies rushing away from them in an expanding, homogeneous cosmos. This is the ultimate expression of cosmic humility. Our planet, our star, and our galaxy are all utterly ordinary, residing in a universe that presents the same face to all its inhabitants. This grand uniformity, born from the fiery, balanced conditions of the Big Bang and preserved over billions of years, is the silent, majestic backdrop against which the intricate drama of cosmic evolution plays out. This seemingly perfect uniformity, however, presents one of the most profound puzzles in all of cosmology, a conundrum so deep it threatened to unravel the entire Big Bang theory. It's known as the horizon problem, and to understand it, we need to think about the most fundamental speed limit in the universe, the speed of light. Nothing can travel faster than light through space. This isn't just a rule for spaceships and laser beams. It's a limit on the transmission of any kind of information, including heat. For two objects to reach the same temperature, they must be in thermal contact, able to exchange energy until they balance out. You can experience this by putting an ice cube into a warm drink. The heat from the drink flows into the ice cube until they are the same temperature. But this process takes time. Now, let's apply this to the early universe. The cosmic microwave background radiation we see coming from the northern sky and the radiation we see coming from the southern sky were emitted from regions of space that were billions of light years apart when the universe was only 380,000 years old. Here's the crux of the problem. In that relatively short time since the Big Bang, there simply hadn't been enough time for light or any form of energy to travel from one of these regions to the other. They were, in cosmological terms, outside of each other's horizon. They were like two people standing on opposite shores of an ocean that is expanding faster than any boat can sail. They could never have communicated, never exchanged a single photon to synchronize their temperature. According to the standard Big Bang model, these regions should have had no way to know about each other's existence, let alone agree on a temperature to within 1 part in 100,000. It would be like walking into a vast, dark auditorium and finding that thousands of people who had never spoken or even seen each other were all humming the exact same note in perfect pitch. The odds of that happening by chance are infinitesimally small. This was a glaring inconsistency that suggested a major piece was missing from our story. The solution to this puzzle is as elegant as it is mind-bending, a theory called cosmic inflation. Inflation proposes that the universe underwent an unimaginably brief period of hyper-fast expansion before settling into the more sedate pace of the Big Bang expansion we observe today. This wasn't an expansion of matter flying through space, but a stretching of the fabric of space-time itself, and it happened at a rate that is truly superluminal faster than the speed of light. Now, this might sound like it violates Einstein's rule, but there's a critical distinction. The law that nothing can travel through space faster than light remains intact. However, there is no limit on how fast space itself can expand. A useful analogy is to think of ants crawling on a rubber band. The ants have a maximum crawling speed, but if you stretch the rubber band itself, the distance between two ants can increase at a rate much faster than either ant could ever crawl. Inflation was the universe stretching its own rubber band at an incomprehensible rate. This brief inflationary spurt is thought to have lasted from about 10 to the negative 36 seconds to 10 to the negative 32nd seconds after the beginning. In that almost infinitesimally short window, a region of space smaller than a subatomic particle was inflated to a size larger than our entire observable universe today. This colossal stretching is the key to solving the horizon problem. Before inflation began, the entire seed of our cosmos was an incredibly tiny volume, small enough for every part of it to be in intimate causal contact. There was more than enough time for this minuscule patch to reach a uniform temperature, to smooth itself out through the constant interactions of its constituent particles. It was like a single, perfectly mixed drop of liquid. Then inflation kicked in. This tiny, uniform and thermally equilibrated patch was stretched to cosmic proportions. The regions that we now see on opposite sides of the sky, which appear to have never been in contact, were once neighbors in that primordial speck. They were once close enough to easily exchange energy and reach the same temperature. The inflationary expansion didn't create the uniformity. It simply took a pre-existing uniformity that was established on a small scale and magnified it to encompass the entire observable cosmos. The horizon problem vanishes because the problem itself was an illusion created by only looking at the later, slower expansion. Inflation provides the mechanism that allowed the entire universe to have a common origin and a shared temperature, preserving the memory of its initial, intimate connection across the vast gulfs of space we see today. The very existence of the stars, the planets, and us hinges on a profound and deeply mysterious victory that occurred in the universe's first second. It is a victory of matter over antimatter. According to every known principle of particle physics, the Big Bang should have been a perfectly symmetrical event. For every particle of matter it created every proton, every electron. It should have created an equal and opposite particle of antimatter. Antimatter is the mirror image of normal matter, identical in mass but with opposite electrical charge. An antiproton has a negative charge, while a positron, the antimatter counterpart of an electron, has a positive charge. And when matter and antimatter meet, they do not simply coexist. They annihilate each other in a flash of pure energy, vanishing from the material world. If the universe had begun in perfect symmetry, this is precisely what should have happened. The countless matter and antimatter particles born in the fiery beginning would have immediately sought each other out, annihilating in a spectacular cosmic conflagration. The result would have been a universe containing nothing but radiation, a featureless, eternal sea of light, devoid of atoms, stars, or any possibility of life. The fact that you are here to ponder this question means that this perfect symmetry was broken. Somehow, someway, a tiny, almost imperceptible imbalance tipped the scales. For every 1 billion matter-antimatter pairs that annihilated each other in the early universe, one single particle of matter was left behind. It is from that 1 in a billion surplus that every galaxy, every star, every planet, and every one of us is made. We are the descendants of the most fortunate statistical fluke in cosmic history. Physicists call the process that led to this imbalance baryogenesis, and it remains one of the most significant unsolved problems in all of science. The quest to understand it is not just about a historical curiosity. It is a direct assault on the fundamental laws of nature. In the 1967, the physicist Andrei Sakharov outlined the 3 essential conditions that any viable theory of baryogenesis must satisfy. First, the universe must have been in a state of thermal disequilibrium. The processes involved could not have been perfectly balanced and reversible. Second, there must be processes that violate the conservation of baryon number. A baryon is a heavy particle like a proton or neutron, and baryon number is a quantum property that is, as far as we can tell in our labs, conserved. You can't just create a proton out of nothing. Baryogenesis requires that this rule was broken in the early universe. And third, the interactions responsible must violate both C-symmetry and CP symmetry. This gets into the deeply strange world of particle symmetries. C-symmetry, or charge conjugation symmetry, means the laws of physics should be the same if you swap every particle with its antiparticle. CP symmetry is a combination of charge conjugation and parity, which is like a mirror reflection. If these symmetries were perfectly upheld, matter and antimatter would behave identically and no imbalance could ever arise. We have actually observed CP violation in certain rare particle decays in experiments, which is a crucial piece of the puzzle. However, the amount of CP violation we have measured in the laboratory is far too small to account for the 1 in a billion imbalance we see in the cosmos. It is off by a factor of about 10 billion. This tells us that the physics we understand in our particle accelerators is not the whole story. The true mechanism of baryogenesis must involve new physics, processes or particles that operated only at the incredible energy scales of the very early universe. Several compelling theories have been proposed. Some involve hypothetical, super-heavy particles known as X-bosons that decayed asymmetrically, favoring matter over antimatter. Others are tied to the physics of cosmic inflation or to the behavior of neutrinos. There is even the speculative idea that the matter excess was not created in our universe, but that our universe is just a matter-dominated bubble in a much larger multiverse that contains antimatter-dominated regions elsewhere. The search for the answer is ongoing at the frontiers of both theoretical physics and experimental observation. Particle colliders like the Large Hadron Collider are searching for signs of new particles or additional sources of CP violation. Cosmologists are scouring the sky for any hint of leftover antimatter structures, like entire antimatter galaxies, which would contradict our current models. The mystery of baryogenesis is a stark reminder that our existence is tied to a fundamental broken symmetry in the laws of the universe. We are not the product of a balanced and inevitable process, but rather the unlikely outcome of a cosmic imperfection. A tiny crack in the mirror of reality that allowed a world of substance to emerge from what should have been an ocean of light. Yet another subtle but potentially profound player was present in the cosmic nursery, a force so familiar to us here on Earth that we often overlook its possible role in the grandest of narratives. Hidden within the turbulent plasma of the infant cosmos, weak magnetic fields may have been woven into the fabric of reality, their ghostly lines of force silently guiding the collapse of the first structures. We are accustomed to thinking of magnetism in terms of refrigerator magnets or the Earth's protective field, but its cosmic origins stretch back to a time before the first stars, to a forgotten fact that could reshape our understanding of cosmic evolution. The question of how the universe became magnetized is a deep puzzle. We observe magnetic fields everywhere we look, in stars, in planets, and threading the vast spaces between galaxies. But where did they come from? One possibility is that they were generated later by the dynamo effect within spinning stars and swirling galaxies, much like the Earth's magnetic field is generated by the motion of molten metal in its core. However, an alternative and more intriguing theory suggests that the seeds for these fields were planted in the universe's extreme infancy, during the period of inflation or the subsequent quark-gluon plasma phase. In these unimaginable conditions, tiny electromagnetic fluctuations could have been stretched and amplified by the violent motions of the expanding cosmos. A process known as the battery effect, where the motion of charged particles in a plasma generates a weak electric current and thus a magnetic field, could have been at work. These primordial fields would have been incredibly weak, a billion times weaker than the Earth's magnetic field, but they would have been present everywhere, a fundamental part of the cosmic landscape from the very beginning. The influence of such a pervasive, if faint, magnetic field could have been significant. As the primordial gas began to collapse under gravity to form the first stars and galaxies, these magnetic fields would have been frozen into the plasma, a concept known as flux freezing. As the cloud contracted, the magnetic field lines would have been squeezed together, becoming stronger and more organized. This would have introduced a new directional force into the chaotic process of gravitational collapse. Magnetic fields can channel the flow of gas, suppress turbulence in certain directions, and even provide a form of additional pressure that supports a cloud against gravity, influencing the final size and shape of the structures that formed. It's possible that the presence of these fossil fields helped determine the characteristic mass of the first stars, or influenced the rate at which gas could cool and condense, subtly imprinting their signature on the entire subsequent history of cosmic structure formation. Detecting these ancient magnetic fields, however, is a formidable challenge. Their original signal is buried under eons of later magnetic activity from stars and galaxies. Scientists are pursuing ingenious methods to find their faint trace. One approach is to look for their imprint on the polarization of the cosmic microwave background radiation. As the CMB photons traveled through the early universe, any large-scale magnetic fields present would have affected the orientation of their light waves, leaving a specific twisting pattern known as B-mode polarization. While the primary source of B-modes is expected to be the gravitational waves from inflation, a component could also reveal these primordial magnetic fields. Another method involves studying the light from the most distant quasars. As this light journeys across billions of light years, it passes through intergalactic clouds. If these clouds are permeated by a weak universal magnetic field, it would very slightly affect the polarization of the quasar's light. By carefully analyzing the light from many quasars, astronomers hope to statistically tease out the signal of a pervasive background field. If we could one day confirm the existence of these primordial magnetic fields, it would open an entirely new window into the universe's first moments. Their strength and configuration would carry direct information about the physics of the universe when it was less than a second old, a period currently inaccessible by any other means. They would be a fossil relic not of matter but of force, a silent testament to the dynamic and electrically charged nature of the cosmos at its birth. Their discovery would connect the magnetism we experience every day directly back to the creation of everything, revealing yet another layer of subtle order and influence in the seemingly chaotic dawn of time. Yet this magnificent story of cosmic evolution, from a searing plasma to a life-giving universe, leads us to a profound and haunting question. If the ingredients for life are scattered so widely, and if the universe has been forming stars and planets for so long, why does the cosmos feel so empty? Why, in all our searching, have we encountered only silence? This brings us to a forgotten fact that connects our deepest origins directly to our existential solitude. The conditions that made our existence possible also created a universe where intelligent neighbors may be the rarest of exceptions. The very timeline of cosmic evolution offers a compelling, if sobering, answer to the Fermi paradox, the famous question, where is everybody? The paradox, formulated by physicist Enrico Fermi during a casual conversation in the 1950s, stems from a simple logical chain. Our galaxy is ancient, roughly 13 billion years old, and contains hundreds of billions of stars. Many of these stars are older than the Sun and likely host Earth-like planets. If even a tiny fraction of these planets gave rise to intelligent life, and if just a handful of those civilizations developed technology and the desire to explore the galaxy, the Milky Way should have been colonized many times over by now. The silence we observe, therefore, is paradoxical. It suggests that something is fundamentally wrong with our assumptions. One of the most overlooked pieces of this puzzle is the sheer unsuitability of the early universe for life as we know it. For billions of years, the cosmos was not a cradle for biology. It was a sterile, hostile environment. Life requires a specific recipe, planets with a stable mix of elements like carbon, oxygen, nitrogen, and phosphorus. But for the universe's first several billion years, these essential ingredients simply did not exist in sufficient quantities. The first stars, those colossal population 3 giants, lived and died in a few million years, seeding the cosmos with only the first traces of heavy elements. It took multiple generations of stars, each born from the enriched ashes of their predecessors, to gradually build up the cosmic abundance of these complex atoms. Our own solar system formed around 9 billion years after the Big Bang, and it contains the recycled material from countless stellar generations. This long period of chemical maturation was an absolute prerequisite for rocky planets and the chemistry of life. An Earth-like planet simply could not have formed in the first few billion years of the universe. The necessary heavy elements were not yet available. The universe had to age like a fine wine before it could host complex biology. Beyond the lack of materials, the early cosmos was a violently radioactive place. The rate of star formation was far higher, meaning supernova explosions, events that sterilize vast regions of space with lethal gamma radiation, were catastrophically common. Any fledgling planet that might have miraculously accumulated the right elements would have been frequently scoured by these apocalyptic blasts, resetting the clock on evolution again and again. Furthermore, the central regions of galaxies, where stars are densely packed, would have been particularly dangerous. Life likely needed the relative quiet and safety of a galactic suburb, like the Orion Spur where our Sun resides, far from the chaotic and lethal galactic core. This combination of factors, a slow chemical enrichment and a gradual calming of the cosmic environment, imposed a significant delay. It created a window of habitability that only opened after the universe was already middle-aged. We are not among the first possible civilizations. We may be among the very first, or even one of the first. This cosmic delay, when combined with the staggering vastness of space and the fleeting nature of technological civilizations, might be the core of the answer. Imagine intelligent species emerging on worlds separated not just by thousands of light years, but by millions of years in time. One civilization might rise, flourish, and fade into obscurity long before another even learns to use tools. The overlap in time between two technological species active in the same galactic neighborhood could be vanishingly small. We have only been broadcasting our presence with radio waves for about a century, a mere blink in the multi-billion-year history of our galaxy. An alien civilization 1,000 light-years away would only now be receiving our first television broadcasts from the early 20th century. If they sent a reply instantly, we would not receive it for another millennium. The Great Silence, then, may not be a silence of absence, but a silence of timing. We are like islands in a vast ocean of time, shouting into the darkness, unaware that our nearest neighbors may have fallen silent eons ago, or have yet to begin their own story. This perspective reframes our place in the cosmos. We are not latecomers to a crowded galactic party. We may be incredibly early arrivals in a universe that has only recently become capable of hosting life at all. The conditions that allowed us to exist, the specific timing of our sun's formation, the peaceful region of our galaxy, the abundance of heavy elements, might be far more special and rare than we ever imagined. The silence is not a cause for despair, but a humbling reminder of our profound connection to the entire cosmic timeline. From the quantum fluctuations of inflation to the fiery deaths of the first stars, every event was a necessary step in a chain of causality that led to a quiet planet where life could finally arise and look up at the stars, wondering if anyone else is out there looking back. This brings us to a discovery that has quietly shaken the world of cosmology, a puzzle that might mean our cosmic neighborhood is not as typical as we once believed. For nearly a century, the Hubble constant has been a cornerstone of our cosmic understanding, a single number that represents the current expansion rate of the universe. It tells us how fast, on average, galaxies are receding from us for each megaparsec of distance, a unit equivalent to about 3.26 million light-years. Determining this number with absolute precision has been a holy grail for astronomers because it not only tells us how fast the universe is growing today, but it also acts as a key ingredient for calculating the universe's age, its size, and its ultimate fate. We have two primary and seemingly foolproof methods for measuring it. The first method looks locally, building a cosmic distance ladder by observing pulsating stars called Cepheid variables and cataclysmic supernova in nearby galaxies to calibrate distances and recession velocities with incredible care. The second method looks to the very edge of the observable universe, using the detailed map of the cosmic microwave background radiation from the Planck satellite. By analyzing the subtle patterns in this ancient light, we can work backwards using our well-tested model of cosmic evolution to predict what the Hubble constant should be today. Both methods are incredibly sophisticated, both are operated by teams of brilliant scientists, and both are believed to be rigorously accurate, yet they disagree. And not by a little, the local measurements give a value that is consistently, significantly faster than the value derived from the primordial universe. This discrepancy is known as the Hubble tension, and it is one of the most significant unsolved problems in modern cosmology. One compelling explanation for this tension is that we are not getting a perfectly average view of the cosmos. We might, in fact, be living inside a local cosmic void, a vast region where the density of matter is slightly lower than the cosmic average. Astronomers sometimes call this a Hubble bubble. Imagine the universe as a vast, gently rolling landscape of hills and valleys, where hills represent over dense regions rich with galaxies and valleys represent under dense voids. Our Milky Way galaxy, along with our local group of galaxies, might be situated in one of these valleys. If our local region has less matter than the universe as a whole, the gravitational pull holding our neighborhood together would be slightly weaker. As a result, the expansion of space would have a slightly easier time pushing the galaxies around us apart, leading to a measured expansion rate that is faster than the true universal average. It would be like trying to measure the average incline of a mountain by standing in a small, local dip. Your measurement would be accurate for your immediate surroundings, but it wouldn't reflect the larger topography. Our local cosmic dip or Hubble bubble would therefore be skewing our perspective, making it seem like the entire universe is expanding faster than it truly is. Of course, scientists are considering other, even more exciting possibilities. The Hubble tension could be more than just a measurement artifact. It could be a genuine signal of new physics. Perhaps dark energy, the mysterious force driving cosmic acceleration, is not a constant as Einstein proposed, but an evolving field whose strength has changed over time. Maybe there is a previously unknown type of subatomic particle, like a new variety of neutrino, that was abundant in the early universe and has subtly altered its expansion history. Or the discrepancy could be pointing to a flaw in our understanding of gravity itself, suggesting that Einstein's theory of general relativity, while spectacularly successful, might need a minor tweak when applied to the universe as a whole. Each of these possibilities would revolutionize our understanding of fundamental physics. For now, the Hubble bubble remains a leading candidate. It serves as a powerful reminder of the Copernican principle, the idea that we do not occupy a special place in the universe. If we are indeed inside a local underdensity, it means our vantage point is not perfectly representative. Our cosmic address, far from being at the center of things, might be in a slightly atypical suburb, and accounting for that slight bias may be the key to resolving one of the greatest mysteries of our time. And so we arrive at our final, and perhaps most humbling, forgotten fact. The story of the universe's origins is not a finished book sitting on a shelf. It is a living document, a manuscript with entire chapters yet to be written, and the final pages are still being composed by the collective efforts of scientists around the world using tools more powerful than ever before. For all we have uncovered, from the primordial symphony to the ghostly grip of dark matter, the most fundamental questions remain wide open, reminding us that every answer we find simply reveals a deeper layer of mystery. What, for instance, is the true nature of the dark universe that makes up 95% of everything? Dark matter and dark energy are placeholder names for profound ignorance. We know dark matter exists because of its gravitational pull, but we have no idea what particle, if any, constitutes it. Is it a yet-to-be-discovered heavyweight particle, a light and feebly interacting one, or could it even be a manifestation of a modification to the laws of gravity on cosmic scales? Similarly, dark energy's accelerating push could be a constant property of the vacuum of space, or it could be a dynamic field that has changed over time, which would dramatically alter our predictions for the universe's ultimate fate. These are not minor gaps, they are chasms in our understanding of reality itself. Then there is the enigmatic trigger for cosmic inflation. The theory beautifully solves major puzzles, but it raises a profound question of its own: what started it? What was the specific quantum fluctuation or physical condition that kicked off that period of hyper-fast expansion? And just as intriguingly, what caused it to stop? The mechanism that brought the inflationary era to a close, transferring its energy into the hot plasma of the standard Big Bang, is a subject of intense theoretical debate. Understanding this transition is key to knowing if our universe is a one-off event or one bubble in an infinite, eternal multiverse. This naturally leads to the ultimate frontier: what, if anything, came before the Big Bang? The question may be ill-posed if time itself began then, but theories like the Big Bounce or conformal cyclic cosmology suggest a pre-existing reality. Proving or disproving these ideas pushes the limits of our observational capabilities, but it is not impossible. The detection of a specific pattern of primordial gravitational waves, ripples in space-time from the inflationary period, could carry imprints from a previous cosmic phase, offering a faint whisper from a time before time as we know it. This is not a story that has stalled, it is accelerating. We are living in a golden age of cosmological discovery, armed with a new generation of observatories that are like time machines, peering deeper into the past than ever before. The James Webb Space Telescope is already revolutionizing our view of the first galaxies, revealing their formation and growth in stunning detail and testing our models of the early universe. Soon, the Vera C. Rubin Observatory will begin its monumental legacy survey of space and time, scanning the entire southern sky every few nights. It will map billions of galaxies, track countless asteroids, and undoubtedly uncover transient phenomena we cannot yet imagine, providing a dynamic, moving picture of the cosmos that will shed new light on dark energy and the structure of the cosmic web. These tools, combined with ever more powerful particle colliders and sophisticated computer simulations, ensure that the next decade will be one of unprecedented discovery. The forgotten facts we've explored today are not static relics, they are active puzzles, each one a doorway to a deeper understanding. The narrative of our cosmic origins is the greatest detective story ever told, and we are privileged to be living in a chapter where the clues are pouring in faster than we can process them. Our journey from a silent, dark beginning to a universe teeming with light and life is far from over. It is an ongoing inquiry, a testament to human curiosity, and a reminder that the most exciting discoveries about where we came from are likely still ahead of us, waiting in the dark to be brought into the light. So, after this incredible journey through 25 forgotten corners of cosmic history, what are we left with? We started with the misconception of a silent explosion and discovered a universe born from a deafening roar. We learned that the very atoms of our bodies were forged in the hearts of stars that no longer exist, and that the space between galaxies is not an empty void but a dynamic fabric stretching faster than light itself in its infancy. We've confronted the humbling reality that everything we can see and touch is just 5% of the cosmic recipe, with the rest being mysterious dark matter and dark energy. We've traced the blueprint for galaxies back to random quantum whispers and pondered whether time itself had a beginning. This collection of facts does more than just update a textbook definition of the Big Bang. It fundamentally transforms our picture of the universe from a static, predictable machine into a vibrant, evolving, and deeply strange reality. It's a cosmos that began as a perfect fluid that may be one of countless bubbles in a multiverse, and whose fundamental laws might have been set randomly during a fleeting moment of symmetry breaking. This narrative is not one of cold, impersonal forces, but of a dynamic drama filled with phase transitions, violent explosions, and patient, gravitational sculpture over billions of years. The universe is not a finished product, it is a continuous unfolding story, and we are a part of its latest, most intricate chapter. This drive to understand where we come from is one of the most profound aspects of being human. For millennia, we have looked up at the stars and told stories about our origins. Today, we are privileged to live in an era where those stories are informed by real data, by telescopes that act as time machines, and by equations that can describe the first moments of time itself. Yet, as we've seen, every answer unearthed by science reveals even deeper and more thrilling questions. The mystery has not been solved, it has been deepened and enriched, inviting us all to participate in the greatest detective story ever told. And that is where you come in. This isn't just a story for scientists in lab coats, it is the story of our shared cosmic heritage. The next time you find yourself under a clear night sky, take a moment to really look. Remember that the faint light from distant stars is a messenger from the past, that the empty space between them is teeming with hidden forces, and that your very existence is the result of a breathtaking chain of events stretching back over 13 billion years. Let that feeling of wonder fuel your own curiosity. We want to hear what resonates with you most. Was it the idea of a universe ringing like a bell, or the ghostly sea of neutrinos flowing through you right now? Share in the comments below which of these forgotten facts surprised you the most, or what other cosmic mysteries keep you looking up at the stars. The conversation about our origins is far from over, and your perspective is a valuable part of it. Stay